It's my pleasure to introduce Vivienne. She's an associate professor at MIT in the Department of Electrical Engineering and Computer Science. Her research interests are in energy-aware signal processing algorithms, and she's here to talk to us about approaches for energy-efficient implementation of deep neural networks. Vivienne?
All right, thank you very much for the introduction. It's great to be here. So today, the goal of in the next hour, what I want to give you guys is an overview of all the various different techniques that people have applied for reducing the energy consumption of processing deep neural nets, from the hardware up to the algorithm portion. And then the last part of today's talk, I really kind of want to emphasize what are the trade-offs that people are making and what are the limitations of the current techniques. So what can we do more to improve them? So just to start off, in terms of the research within my group, and actually probably one of the motivations why you guys are here, is that we like to primarily focus on the processing of video, because we believe video is the biggest of the big data. So I'm sure you guys already know that the internet traffic is dominated by video, and the amount of video that's being generated every day is more than what humanly we can actually watch. A lot of this video is being collected on battery-operated devices like cell phones. But due to the limitation of the energy that's available there, we often have to push it to the cloud. But this is not ideal for cases where you care about latency or privacy, or if you have limited communication bandwidth. So really, we want to try and be able to do a lot of the processing on the edge device. And that's really the focus of the overarching research within my group, is how do we do energy-efficient pixel processing? So that's the context of what we care about. Today, one of the most popular forms of processing that you actually want to do on this edge device would obviously be deep learning. And one of the driving reasons for that, of course, is because deep learning is offering significantly higher accuracy for a variety of computer vision tasks as compared to traditional handcrafted methods, right? So you all must have heard about, for example, starting in 2012 with AlexNet coming from the University of Toronto. On this ImageNet competition, it showed substantial reduction in terms of the error. So in this plot, lower the better. And then since then, the error has dropped to, in 2015, it actually achieved an error rate that's actually below the error rate or actually beat human level accuracy. The challenge for all of this, of course, is that even though it's great to reduce the error rate, the challenge is that we actually require a lot more computation. So on these devices, we don't just care about accuracy, but we also care about energy, speed, and cost. And so this deep learning has become a real big challenge for this particular space, even though we know that for a wide variety of applications, it actually is giving us much higher accuracy. So I'll give you a very brief overview in terms of what deep learning is, specifically deep convolutional neural nets, which is the type of deep neural net that we typically use for visual data. I know some of you may be already familiar with this, but I'd just like to walk through it because there's a lot of different terminology that typically is used to describe neural nets, so I just want to make sure that we're aligned before I get into the details. So we know that modern deep neural nets, and the ones that are achieving really high accuracy, tends to have a lot of convolutional layers, potentially up to 1,000 convolutional layers, and then it typically is followed by 1 to 3 fully connected layers, particularly for an image classification task. Now, what really stands out if you're trying to build hardware or trying to really address the complexity of the neural networks is that you realize that most of the operations or most of the complexity actually comes in the convolutions. In fact, convolutions account for more than 90% of the overall computations. They dominate both the runtime and the energy consumption. So if you're going to look at designing any specialized hardware, or if you're going to look at optimizing the algorithm, this is where you really want to focus your attentions. So I'll briefly walk through what's actually going on within each convolutional layer and understand why is it very complicated. So for example, you start off with a simple 2D convolution. So you have a 2D filter, which contains the weights. And then you have a 2D either input image to your neural net or input feature map if you're talking about different layers. And really all we're actually doing is we're doing an element-wise multiplication of the filter to this input feature map. And then we sum up the values and we get one output activation or one output pixel. And then you apply convolution, so it's like a sliding window where you apply the filter across this input feature map. Now, if you've taken any image processing class or if you've done image processing before, you know that we've been using this type of 2D convolution for decades. There's nothing particularly special here. We use this for a lot of different types of image processing. So the real question we want to ask is, why is it more complicated for deep convolutional neural nets? And really, the complexity of this stems from the fact that we have to move to higher dimensions. So for example, rather than just applying one filter, you're applying multiple filters to the actual image. And furthermore, in each of these filters, it's actually not just, let me just use the regular pointer. It's not just a 2D convolution, but you actually have multiple channels as well. So you can think of the channels as, for example, in your input image, it would be your red, green, and blue components. And then you have to do a 2D convolution for each of these channels for them to add up to one value. And then furthermore, you have to apply many of these filters to your input feature map so you generate an output that also has multiple channels. So you're increasing the dimensionality in terms of the number of channels, and you're also increasing the number of filters you're actually applying to an input image. And that's why the dimensionality of the problem increases. And of course, if you're processing more than one particular image, we would call it image batch size. This will also increase the number of outputs you might have. And typically, for given hardware, the number of image batch sizes is between 1 and 256. But the main takeaway I want to give you guys is that basically we're looking at these very high-dimensional convolutions that are necessary for deep convolutional neural nets. And to give you an idea of the sizes, for example, if we look at AlexNet, which was the winning network back in 2012, we can see that, for example, in layer 1 to 3, we're talking about tens of thousands to hundreds of thousands of weight parameters in the filter itself. So this is the data not just of the images that's going through, but this is the number of weights you actually have in the filter itself that you have to manage. And in terms of processing, the processing that you actually have to do, you're talking about hundreds millions of max or multiplies and accumulates. Right? And this is to process an image for these type of image classification tasks. The input image is around 224 pixels by 224 pixels. So you should really think about how this would scale if we're starting to talk about high dimensional or high HD images. So that's one thing that makes it challenging. The filter shapes are very large. The other, with a lot of computation. The other challenge that we face is that the filter sizes and the number of filters and number of channels actually change substantially from layer to layer, right? So if you're familiar with building hardware, you know that often if you can hard code something, it's going to be much more efficient. But this poses a challenge for neural nets because you can't hard code the filter shapes, right? So for even within one neural network, there's a variety of shapes that you can support. And then we're talking about many different types of neural networks today. So you need to be much more flexible to do that. And of course, you want the weights also to be programmable. So AlexNet is one particular example of a popular neural net. And then since AlexNet back in 2012, as I mentioned, there's been an increasing number of neural nets that come about from Overfeet, VGG, GoogleNet, and then ResNet in 2015 from Microsoft, which is the one that beat human-level accuracy. I also want to point out that the concept of convolutional neural nets has been around since the 90s. So Jan LeCun did some foundational work on this in the early 90s. So there's a LeNet that you might be familiar with, which is a very small convolutional neural net. And then since then, because we've had a lot more compute available and a lot more data available, we've had these much more larger scale networks. So what is the important trend that we can take away from all these popular DNNs? So shown here is a table for all of them. So here's LeNet, AlexNet, VGG, GoogleNet, and ResNet. And you can see that in terms of the error rate, they keep on going lower. But the main thing, since we don't have time to walk through every single detail about this, that we want to take away is that you can see that the number of convolutional layers is increasing, so the networks are becoming deeper. And in terms of the fully connected layers, they tend to be reducing. So now, it's very standard for GoogleNet, ResNet, and other neural nets that have come along after 2015 only have one fully connected layer. So the message for this is that the convolutional layers, particularly in CNN, are becoming increasingly important. And we need to find ways to process them more efficiently. You can also see that in terms of the max, people have been trying to, so VGG jumped up significantly, but then since then it's been around 1.5 to 3.9 billion max for the whole inference pass. The other thing I just want to emphasize is that there's actually kind of two stages for DNNs. One is the training stage that you often hear about, whereas you have a very large data set that you use to train the neural nets. And by training the neural nets, what we actually mean is determining the weights that we would use in those particular filters. Then what you would typically do is you would, and this often happens in the cloud or the data center, and then what you would do is you would download those weights to your edge device, for example, so your phone, your drone, your car, and then you perform what we would call inference, which is the weights are now fixed, they've been trained, and now what we do is we give you an image, and then based on all these weights, you can tell me, what's the object in the image and so on for a particular task. And so the main focus of my talk today will primarily be on the inference side of things, though some of the techniques that we talk about could be extended to training, but given the limited time, we're going to focus on inference. The other really important thing that I hope you guys take away from this is what are the key metrics that we can use to evaluate different deep learning solutions or systems. I'll spend a little bit more time on this at the end of the talk, but really there are several key metrics that we really have to balance. So the first thing, which is really important, is accuracy. Because why are we very excited about this concept of deep learning? It's because it's giving us really great accuracy. That's why it's kind of had this resurgence over the last 5 to 6 years. But in terms of accuracy, it's important to define what the data set is, what kind of DNN model are you using? Are you using AlexNet or using LeNet? Because some of these tasks or some of these models are very different in terms of their complexity. Programmability, as I mentioned, is also really important because you have to support different DNN models. And maybe also support different weights, filter weights. So often, even if you have one model, you might fine-tune the weights for a different task or a different data set. So that flexibility is really important. And we're going to really talk about why this is an increasing challenge now, even more so than it was maybe 3-4 years ago. Energy and power is also really important because we're talking about edge devices. And here, it's really important to consider both the energy of, let's say, your ASIC or your processor itself, and the processing power or the power consumption of off-chip devices like the DRAM, right? So often, as it turns out, the DRAM of these off-chip memories actually consume more power than the processor itself. So it's really important to look at the whole system power. Throughput and latency is obviously important, so you want to see how quickly you can run. And then, of course, cost is very important as well. And typically, we mean the area cost of the die, for example, the memory or the logic size. So given the amount of excitement that there is in deep learning and the wide range of applications that it's currently serving, there have been a lot of, in addition to custom hardware, which we'll talk about a little bit later on, but even in the current programmable platforms, there's been a lot of emphasis on targeting, making GPUs and CPUs more targeted towards deep learning. So for example, Intel has an offering of Xeon Phi where they have more specified instruction sets for neural nets. And of course, we know that NVIDIA has come up with multiple series of high-performance GPUs that can do impressive things for deep learning. The main kernel or the main functionality of how these CPUs and GPUs process these neural nets is by using or exploiting their matrix multiplication libraries. So basically, the main question is, can we take these large neural nets and then map them into a matrix multiplication so that we can leverage a lot of the existing infrastructure that's already in these CPUs and GPUs. In particular, they already have matrix multiplication libraries for CPUs and GPUs that really accelerate this type of operation. If you can basically put it into a matrix multiplication format, you can use these libraries, OpenBlast or Intel MKL to really speed up, or use DNN to really speed up the processing. And of course, there's other optimizations from a software level where they look at tiling based on the storage hierarchy of the CPU or GPU itself, which basically means that based on how much memory you have at the different levels of the memory hierarchy, how much work do you grab at a specific time. In terms of how you take that large convolution that we said and map it to an matrix multiplication, basically what they do is they expand it into what we call a Toeplitz matrix. So if we look up here at the convolution itself, if you remember from the example above, if we have a 3x3 input feature map and a 2x2 filter, we basically take this 2x2 filter and move it across the input feature map and generate an output feature map that's also 2x2. So what they do to make it a matrix multiplication is they expand it with the Toeplitz matrix. So this 2x2 filter now becomes a 1x4. And then the input feature map, we do this Toeplitz expansion. And you can work this out later at home. And so as a result, and then the output is going to be a 1x4 vector. And as a result, you're just doing a dot product or a vector matrix multiplication. The one trade-off of this, of course, is that you can see in the Toeplitz matrix, when you're expanding the input, there's actually going to be repeated or redundant data in the matrix. So you're losing some form of data reuse that's going to be there, and data reuse is going to be really important, and we'll talk about that later. But in general, there is some inefficiency for this representation, but the benefit of this representation is that you can use all those really fast and efficient matrix multiplication libraries. And so a lot of the optimizations that have happened on CPUs and GPUs over the past couple of years is different ways to reduce the number of operations on those platforms to do this matrix multiplication to speed it up, right? And so the goal is that can we take this matrix multiplication, do some form of transform to it, so we can have bitwise the same results, minus some numerical precision issues, but also reduce the number of operations, right? So mostly in all of this work, we focus on, for the CPU and GPU optimization, we focus on mostly on compute, reducing the amount of computation. And so to give you a flavor in terms of what these transforms are actually like, we can actually look at Gauss's matrix multiplication algorithm as an analogy. So we start up here. If you remember the algorithm, basically you're doing an imaginary number, so a plus b, there's a real and imaginary component, times c plus di, and then the outcome would be something like this. And so to perform this computation would actually require 4 multiplications, so AC, BD, BC, and AD, and then 3 additions. So you have a negative here, plus here, and a plus here. The way that you can actually speed this up, we all know that multiplications are more expensive than additions, is to reduce the number of multiplications. And what you can do in this Gauss's matrix multiplication algorithm is that you can pre-compute or compute 3 intermediate values. Rather than going straight from here to here, you can compute 3 intermediate values. So for example, K1, K2, K3 here, and then combine them afterwards. And by doing it in this order, rather than having 4 multiplications and 3 additions, we now only need 3 multiplications and 5 additions. So basically, you're reassociating the data or the computation you have to do in a different order so you can save some of the multiplications. And that's the overall goal here. Often one of the challenges is that you're reducing the number of multiplications, but you're increasing the number of additions. But since multiplications tend to be more expensive, this is really the focus of a lot of these optimizations. And so there are various different techniques that people have used to do these type of transforms. So the most popular is the Winograd transform. You might have heard of it at another talk here. And so this is an old transform that was kind of, again, rediscovered back in 2016 for this particular application. But in general, if you look up Winograd, many, many decades ago. But the idea is that if you apply this transform to your filters and to your inputs, particularly if you're targeting, for example, a 3x3 filter, you get about a 2.25 speed up in terms of your processing. The one challenge for Winograd is that you need specialized processing depending on the filter size. So the transform itself will change depending on the filter size itself. We also have fast Fourier transforms. So if you've done any image processing, you know that typically we want to move to the Fourier space with a fast Fourier transform, and it tends to be much faster. And of course, when you do a Fourier transform compared to direct convolution, rather than being to the power of 4, you're now to the n to the power of 2 log n. And that's typically the benefit of doing FFT. Of course, the cost there is that you're increasing the storage requirements. Because typically, for example, you need to pad up. You have to make sure that your filter and your image, in this case your feature map, are going to be the same size. So you need some kind of padding, and then you have to go into the frequency domain. So there's a storage cost for doing an FFT. And then a little bit less popular, but still relevant, is a Strassen approach. This is typically used for very large sparse matrices. But again, you can do some kind of transform to it so you can reduce the overall complexity. And there are some challenges with numerical stability. And so if you look at, for example, the performance of various NVIDIA GPUs over the past couple of years, part of it is, of course, increased basically speed from the hardware itself, so going from K0 to P100. But also, as they're continuing to improve the various CU-DNN libraries, this is what it's actually exploiting. These new transforms to really reduce the number of operations you have to do that matrix multiplication, right? And typically, I don't have the slide here, but depending on the filter size, you might use a different type of transform. Okay, so that's kind of how that type of transformation feeds into the products that we have out there today. So this is the best that we can do with CPUs and GPUs, and there's a lot of effort in this space. But more recently, there's been a lot of effort to push for specialized hardware, or we refer to them often as accelerators for DNN. So now I'm going to talk about some of the design principles that we want to consider for specialized hardware. So if you can actually change the hardware itself, how would we build this hardware? So we know there's a couple of promising properties of DNN. First, the operations are highly parallelizable, right? They're just a bunch of multiplies and accumulates. There's nothing really else that's really earth-shattering that's going on there, and that's, of course, why they do so well on GPUs, for example, and with SIMDs on CPUs. So high throughput is really possible, and that's really great. The real challenge, though, when we're building hardware is actually the memory access. That's really the bottleneck. So I'll give you an example. So for example, if you're doing a multiply and accumulate, you're going to need, for one MAC, you're going to need to have 3 inputs, the filter weights, the image pixels, and the partial sums. And then you're going to have one, so 3 reads and then 1 write, the updated partial sums. So this is a 4-to-1 ratio in terms of reads to writes. And then furthermore, we know that data access can be very expensive. So in the very worst case, you would actually never do this, would be if you would access all your data from DRAM. And then the energy cost per access in the DRAM is 200 times larger than the computation of the MAC itself. So it's much more expensive to read the data and bring it to the multiplier and accumulate engine than to do the computation itself. And so that's really the challenge that we face, both in terms of energy and in terms of throughput. However, all is not lost. There are various opportunities for what we would call data reuse, meaning that if I move the data onto the chip, I can reuse it multiple times for multiple operations. And we've broken it down to 3 key kind of buckets of reuse that you can have. First is convolutional reuse. So when you're doing convolutions, you use the same pixels and weights, just in different combinations. We also have image reuse, so we apply the same different filters to the same image. So you're going to use any pixel that you're loading, you can use it across filters. And then we also have filter reuse, where we have one filter applied to multiple images. There's 2 different types of architectures that you can pick to do this type of processing. One is temporal architecture, and this is what you would find in a GPU or a CPU, where you have a bunch of ALUs that are doing these multiplies and accumulate in parallel. They share the same control, and they share the same register memory. An alternative hardware implementation, which is typically more popular when you talk about dedicated hardware, is a spatial architecture. And the idea here is that we distribute both the control and the memory across to each of these engines. And then when we're talking about small memories, we're talking about 0.5 to 1 kbytes of memory, so very small. But then you have the memory close by, and you can read from this memory. It will be very cheap. And then you also allow for inter-PE communication. So each of these processing elements can talk to each other. And so this minimizes the amount of data movement or having to go to the expensive memory. And again, I can't emphasize enough that data movement is very expensive, right? So for instance, if it's 1x to do some multiply and accumulate, reading from that very small memory is also 1x. Reading from your neighbor is 2x. Reading from a larger memory is maybe 6x, and then going off to DRAM is the most expensive at 200x. And so you really want to avoid to do that. So the real challenge we have is that how can we take this very large neural net, map it onto this architecture so that most of our reads and writes come from these low-cost memories. And so there's been, as you may know, there's been a lot of work in this space. And there's been a couple of different approaches people have taken. And so we like to categorize them and describe them to you. So first is what we could call weight stationary. And the idea here is that says, I'm going to, for that little memory that I have in each of these processing elements, I'm going to store the weight. And so that weight, it's very cheap for me to read this weight, right? So the weight energy is really reduced. The challenge, of course, is that the activation or the pixel information is moving around in the system a lot, and so is the partial sums. And so this type of data flow can be found in a lot of works, including Google's TPU. An alternative strategy is what we would call output stationary. And the idea here is that, OK, forget about the rates. I actually care more about the partial sums because I have to both do reading and writing to it. And so I want to keep the partial sums, in other words, the computation of the output locally within each of the processing elements. But as a result, all the weights and the pixels now have to move through the system, and that becomes very expensive. Finally, a third strategy some people take is they're like, well, these small memories are very inefficient, actually. So if you are familiar with SRAM design, you know that the area per bit is going to be very inefficient the smaller your memory is because the overhead is not amortized. So rather than having these small memories, I'm going to use all of that area on my chip and make this one huge global buffer. And what that means is that overall, my chip can store more data on chip, and I reduce the DRAM access. Of course, the challenge is that I have a lot more data movement that happens on chip now. A fourth approach is something that we developed within our group. We call it the row stationary data flow. I don't have time to get into the details of it, but the main idea is that, as you might have noticed in the previous few examples, the focus was either reducing the weight energy or reducing the partial sum energy. And really, what we're advocating is that all these different data types really matter. So if you want to reduce overall energy of the system, you have to count for all the different data types. And this is what the row stationary does. It looks to reduce both the weight energy as well as the input and output feature map energy. And so as a result, when we compare the energy consumption of these different data flows, so we have the weight stationary approach here. You can see that the weight energy shown here in the green is the smallest. When you compare it to output stationary, here the red part, the partial sums, is the smallest, and that's by design. But you can see that there's trade-off in terms of, for example, weight stationary, the input pixels and the partial sums are larger, and for output stationary, the weights and the pixels are larger. And in the row stationary case, as I mentioned, we really focus on reducing the data movement of all the different data types that are associated with DNNs. And so you get about a 1.4 to 2.5x lower energy compared to the other data flows. This particular data flow, we wanted to demonstrate it on actual custom hardware itself, so we built an accelerator called Iris, and it has an array of 14 by 12 PEs, so 168 PEs, and we actually fabricated a chip in 65 nanometer and built an actual system on it. If you want to know more about this, you can go to the Iris website. If you just Google this, it will show up Iris and MIT. But in general, just to compare in terms of comparing to mobile GPUs out there, it's about 10x more energy efficient. It runs AlexNet at 35 frames per second while consuming around 278 milliwatts. So taking a step back, so I know this talk is more about deep learning, but if I were to take a step back and if I were a computer vision person and I really just, at the end of the day, cared about what is the energy versus accuracy trade-off for a given task, what would this look like? So this is a plot of accuracy is linearly shown here, and this is the average precision. This is measured for an object detection task. And then shown here vertically is the energy consumption on an exponential graph. And here we have measured results from two different chips that we've designed within our group. So one is the Iris chip doing deep neural nets, and the other is doing object detection with deformable parts models, primarily leveraging the HOG feature. And so these were done by students, both the PhDs in my group, for around the same time, so we could try to keep this test as accurate as possible. But you can see that in general, while HOG, for example, these handcrafted features are less accurate than AlexNet or VGG, you get higher precision with those, there's a significant gap in terms of energy consumption between all of them, even if you build customized hardware. So we're talking about a 300x difference in terms of energy from HOG to AlexNet, and over a 10,000 difference between HOG and VGG. And this is even for custom hardware. So as someone who's building systems, you have to ask, am I willing to have the battery life of my system die 300 times to 10,000 times more for about 2x or 2.5x increase in terms of accuracy? So there's this fundamental trade-off there. And just to give you guys a reference in terms of what these energy net values mean, so video compression, which is basically there for most, at the back end of most image sensors out there, it typically is around 1 nanojoule per pixel. So you can actually see with HOG we're within that bucket. So for the same energy that you would spend for compression, which we do all the time, you can actually understand the pixels, but certainly running deep neural networks is actually still much more complex despite custom hardware. So the question is, what can we do to further lower this energy consumption and help try and close this gap? So the other thing that we can do is we can actually move up and start looking at the DNN algorithms or models themselves. So can we redesign the algorithms to make them more efficient? So there's actually been a huge amount of work in this space. I can loosely categorize them into two categories. The first one is looking at reducing the size of the operands for storage and compute. So this is dealing with things like reducing the bit width, switching to fixed point, and so on. And then the other is actually not just reducing the size of the operands, but reducing the number of operands or operations. And this can be looking at things like exploiting activation statistics, network pruning, and compact network architectures. So I'll talk a little bit about each of these. So the first is in terms of one of the prevailing questions that was asked for a while, which is what is the bit width that we actually need? For inference, we've seen various commercial products that are looking at 8-bit integer, right? So both NVIDIA and Google's TPU back in 2016 announced that 8-bit is enough for them for their inference. In research, however, people have obviously pushed even further. So you have people reducing the number of bits looking at binary nets. So there was some work back in 2015 looking at that, and people have built on top of that. There's also been a lot of work reducing the number of unique weights, right? So if you can reduce the number of unique weights, you can also code your things in a little differently with fewer number of bits. So there's some work on ternary weights and XNOR nets you might have heard of. And then finally, there's been some work looking at nonlinear quantization. And the idea of that is this. So if you look at the distribution of your weights, you can do linear quantization, but typically you want to put your boundaries where you have the most data. So if you use nonlinear quantization, for example, log2, which tends to be very nice because then you can make your computation just shifts, you can do a little bit better. So this is some work, the log network from Stanford, which has shown that this is in fact feasible. So precision is something that people have been pushing. Another thing that people have been looking at is exploiting sparsity, right? So as it turns out, particularly when you look at convolutional neural nets for image processing, we tend to use a nonlinear function called the ReLU, a rectified linear unit. And what it basically does is it sets all the negative values to 0. And so zeros are actually great. You can actually exploit these zeros. Just to also mention that as you go deeper in the network, you tend to have more and more zeros. So shown here in the blue is the typical number of activations you would have. And then the number of non-zero activations in red, you can see that that decreases as you go deeper in the layer. So what can you actually do to exploit these zeros? Well, there's a couple of things that you can do. So in the iris chip, for example, one thing we do is that we skip the memory access and the computation when the activation is 0. Because anything times 0 is going to be 0, so you don't have to do that computation, and you also don't have to even read the weight for that information. And that gives you a 45% energy savings. Another thing that you can do is, as I mentioned, moving data is also very expensive. So you can actually, if you can use these zeros and compress it and reduce the amount of data that you have to move around, it's also very beneficial. And you can see if you do a very lightweight compression using run length coding, on the activations, you can get up to a 2x reduction in terms of the DRAM access. And as we mentioned here, DRAM is very expensive. So this is in the activations itself that naturally happen. Some other work is actually looking at the weights. And so again, back in the late 80s, so Jan LeCun looked at different ways since he was looking at neural nets, how to reduce the amount of weights in the neural net. So he looked at some work called optimal brain damage, and the idea was that he wanted to remove the different weights of the neural net. So can I take a neural network, remove some of the weights, and then retrain it? So by weights, he means parameters, and retrain it and still have the same accuracy. So for him, accuracy was measured in mean squared error, and parameters is number of weights, and he was showing here that in this work, yes, indeed, you can actually do that, right? I can reduce the number of weights and still maintain accuracy as long as I do a little bit of retraining. Then, I guess you could say, 26 years later, we looked at, so there was some work coming out of Stanford looking at, yes, you can also do this with the larger neural nets itself, right? So you can take these very large neural nets, do some pruning, remove some of the weights, and then you can shrink the number of weights that are necessary. So for example, in AlexNet, they were able to show that for convolutional layers, you get about a 2.7x reduction in terms of the number of weights. And in the fully connected layers, you actually get a significant reduction of almost over 10x. And then if you look at the amount of reduction itself in terms of multiplies and accumulates, you get about a 3x reduction. Another approach that people have taken is network architecture design. So can I actually change the filters that I'm actually going to use for this neural net? And so really the trend has been to see if rather than using these large filters, can I build them with a series of smaller filters? So for example, a popular work from GoogleNet is they take a 5x5 filter and they can actually decompose it into two 5x1 filters, or these are separable filters, and then you apply these sequentially. And I would say that actually this, again, is kind of a rediscovery of a technique that is well known. So when I teach an image processing class, we actually cover this in the very first week of class, separability. But again, it's shown to be very useful here in neural nets. Similarly, for VGG, you can take a 5x5 filter and decompose into two 3x3 filters and apply them sequentially. So the idea is that you're reducing the number of weights and you're reducing the number of computations. Finally, another really popular approach is to use what we call a 1x1 bottleneck. And the idea here at a very high level is talking about reducing the number of channels that you actually have in your neural network. And so ResNet, for example, uses this. So they have, rather than applying two 3x3 filters, they actually compress. They apply a bottleneck here where they reduce the number of channels before they apply the 3x3 filter, and then afterwards they expand it. Similarly, GoogleNet does this as well. So you can see before all the convolution, it applies a one-by-one convolution to reduce the number of channels. And then SqueezeNet is some work that does this to the extreme, and they really apply a lot of these one-by-one convolutions in what they call a fire module so that it can significantly reduce the number of weights in a neural network. So as you can see, this is kind of a very big whirlwind in terms of a lot of the different techniques people are using. So we've been looking at this over the past 2 years, and we've put together various tutorial materials. So if you want to have like a much more slower paced version of what we're talking about today, I would recommend looking at these tutorial slides that we put in. This is usually for a one-day tutorial. And then we also have, this is like a 30-page survey that discusses this material. But through putting in these kind of tutorial and survey papers together, we actually discovered that there are certain limitations to these existing approaches, even though there's a huge amount of work in this space. So the first question that we ask is, in the design of efficient DNNs, as we talked about, there's pruning, there's compact networks, there's reduced precision. A lot of this work really focuses on the number of max and weights, right? Which is great, but I think one of the questions that we personally have is, does this translate to energy savings, right? How does this work? So we actually built an energy evaluation model, because it's actually not straightforward to figure out what the energy is. So we built an energy evaluation model that takes in different DNN shapes and different weights and input data, so it counts for sparsity, pushes it through this model, and you get an energy breakdown for the different layers, and you have an idea about in terms of where the energy is actually going. And then one of the key observations that came out from this is that the number of weights alone is not a good metric for energy. And the reason for that is, again, the message I want to get across is when we look at the energy consumption, weights are only sometimes like only 22% of the energy. You actually should look at all the other data types as well. So for example, feature map is also very important, right? So the main message here is that all data types should be considered when you're looking at data flow or energy and so on. Another thing is looking at the concept of pruning. So I'm showing here energy consumption on the x-axis and then accuracy on the y-axis. So to the upper and left is better. So shown here in the blue are different networks that have not been pruned, so they have dense weights. And so as I mentioned, one very effective way of reducing the number of weights is to remove the weights that are small. So this is what we call magnitude-based pruning. Based on your magnitude, you remove the weights. And then you can see, shown here in the green, is that you get to basically maintain the same accuracy, but you reduce the energy. However, in what we're kind of thinking of in our work is that you can extend this and do better. What you can do is actually, rather than just removing weights that are small, why don't you remove the weights that consume the most energy? That would directly target what the energy objective that you care about. And so what we do is we take that energy modeling tool, and it allows us to sort which layers consume the most energy, and then you prune the layers that consume the most energy first. Because you know that as you prune more and more, as you remove more and more weights, it becomes much more difficult to maintain accuracy, right? So you want to remove the weights where you're burning the most energy. And so as a result of that, this energy-aware pruning, shown here in the red, you can see that for the same accuracy, you get even more energy savings. So even compared to, let's say, a magnitude-based pruning for AlexNet, you get about 1.7x reduction in energy for the same accuracy. And the main message for all of this work is really emphasizing that we should target the metrics that we directly care about. So if you care about energy, you should directly target energy and incorporate it into the optimization of the DNN for greater energy savings, as opposed to selecting proxies like max or weights. Now, one of the challenges in this particular work is that we need to use that energy model, and energy models might not always be available to use. So another thing that you can do, and this is in collaboration with Google's mobile vision team, is actually to automatically adapt the network based on empirical measurements from the hardware. So this is some work that we recently put up on arXiv called NetAdapt. And the idea is that you start out with the pre-trained network, right? And you put in various network proposals, and with this optimization loops, we take empirical measurements from, let's say, a phone, and we use that, like for example, latency or energy, and we use that to guide basically the adaptation or the network architecture of the pre-trained network, how we would maybe, for example, do the pruning, and then as the result, you get an adaptive network, which is much more efficient for that particular metric, either latency or energy that you actually care about. And to give you a feeling in terms of how this actually does, again, this is the latency shown here at the bottom, and then this is the accuracy shown up here. And as you can see, the NetAdapt is shown here in the red. And then MobileNet, which is a very efficient network that Google has developed for their mobile devices, as shown here in green. And then you can see that with, basically NetAdapt, you can basically boost the inference speed while maintaining accuracy. And sometimes the accuracy goes up a little bit. So you get about 1.6x or 1.7x faster inference while maintaining the same accuracy. And this is really driven by the fact that you're feeding in latency measurements to derive the design itself, as opposed to counting the max or the weights. Finally, so that's what we have to do for algorithms to make them more efficient. The other challenge is for the hardware itself, right? So now we have, since 2012 when we had the big AlexNet stuff, now there's been a lot more work, as I mentioned, on network pruning, compact networks, and reduced precision. But the real challenge that hardware designers have is that you have no guarantee in terms of what kind of algorithm is going to be run on your hardware. Right? At runtime, you don't know what someone's going to load on your device unless you own the whole stack. So you really need to have very flexible hardware to manage this. And then the challenge is that in a lot of the existing designs, they typically exploit certain properties of the neural net in order to get high efficiency. So a very typical architecture that you would see for deep neural networks, specialized hardware, is to have a MAC array, and then you have a weight memory and an activation memory here. And the idea is that if I read one weight, I can use it across multiple times across the array. If I read one activation memory, I can reuse it multiple times across the array. The challenge for this setup is that the number of reuses, or how much you can reuse across the array, depends on the number of channels that you have, the size of the feature map, and the batch size. Right? So these are two possible configurations that people have been using a lot in order to exploit this reuse. And this is not going to be efficient across all networks that are out there. So we've seen a lot of nice compact neural nets that don't have a lot of channels or don't have very large feature map size or filter sizes. And as a result, they wouldn't be able to fully utilize the array. To provide a more kind of systematic way to characterize these properties, we've also recently published, or in submission, put together a piece of work we call iExam. So this is inspired by Iris. And the purpose of this kind of systematic way is to evaluate how each architectural decision will affect the performance of the DNN. So it captures not just the number of processing elements, but it also captures how you're actually going to use the array itself and all the various different impacts that design decisions that might affect the speed of the neural network hardware. And so the main message I want you guys to take away from this is that it's really important that often people quote in their specs the theoretical peak performance, but it's actually very difficult to hit based on the number of processing elements or number of max, and it's actually often very difficult to hit this. There's many different steps in the design that will actually make your performance much lower than that. Okay, so it's important to ask deeper than the peak performance. And this is what we're trying to find a systematic way to showcase that. To address all these problems, we've recently completed what we call Iris 2. And really, it's focusing on supporting a wider range of filter shapes, both large and compact, supporting different layers, convolution and fully connected, and then a wide range of sparsity. All right, so in the last 7 minutes or so, I want to say a couple of things in terms of how we should compare a lot of the different works that are out there in terms of DNN hardware. So these are what we would call benchmarking metrics. And again, if you want to read more about it, we're going to talk about it we talk a lot about this in our survey paper. And I think this is, if you take away only one thing from this talk, I would say that this is an important thing to take away so that you can actually evaluate all the different solutions that are currently out there for whatever your application might be. So again, the very first thing is accuracy is really important, right? So the quality of result for a given task, people should outline what that is. Throughput's also important. If you have a high amount of data, you have high volume, or if you need to have real-time performance for example, video 30 frames per second. Latency is also really important. So for interactive applications or autonomous navigations, low latency is key. Energy and power are important. So energy is important for the edge devices because of the limited battery capacity. In data centers, power is also really important because that basically puts a limit in terms of how much compute you have, because they need to, high power means more heat dissipation, so it affects the cooling cost. And of course, hardware cost is also very important. So sometimes some solutions say, I'm going to have a huge amount of memory on chip, and you have to decide whether or not for your particular application that cost is feasible. But so the real challenge is balancing kind of these 5 different metrics. And I encourage you to dig deeper when you're evaluating these metrics. So for example, for accuracy, rather than just saying what is the accuracy for what task, you should also say, what is the difficulty of the data set? So for example, digit classification versus image classification is very different in terms of complexity, right? So if someone just comes to you and just tells you an accuracy number, that's an insufficient piece of information in terms of telling you how good their system actually is. The throughput is also important. So as I mentioned before, number of cores alone is not enough. You should also include the utilization along with the peak performance. And ideally, what they should tell you is the runtime of a specific DNN model, not just, this is the number of PEs I have, and this is my clock rate, and this is my peak performance. So you would actually ask, for these particular DNN models, what is your runtime? Latency is really important, so it depends on what the batch size is. Typically, for some applications, you can't maybe group too much data together in before you're running it because you need interaction. Energy and power. So again, you want to have the power consumption of running a specific DNN model, and also you want to ask about external memory access, because as we saw, going to DRAM is really important. So I don't really care if your chip is very low power, but now your DRAM power is very high. And then hardware cost is also important. So what is the on-chip storage you have, number of cores, chip area, and process technology, right? So sometimes, this is maybe a little bit more in the academic space, people report oh, my chip is however square millimeters, but they don't say what process it is and so on, and the cost of that. As an example, these would be some metrics that we would have for the Iris chip. You would talk about the process, so it's in 65 nanometers, the core area, the on-chip memory, number of multipliers. We even go down to core area per multiply and so on. You also want to see if it's measured or simulated. So those of you who have ever done chip design, there's a big difference between measured and simulated, because when you measure the chip, when you tape out a chip, you actually have to build in a lot of margin into it to make it work, but then it actually works. But it is a big difference. So you should always ask for that if someone quotes you a spec. And then when it's actually demonstrating a performance for a given model, you should talk about what model you're using. For example, AlexNet. What is the accuracy of that particular model? What are the supported layers? So for example, in Iris V1, we only support the convolution layer, so we should state that out. The number of bits per wait, activation, batch size that you're using, runtime, power, and also off-chip access per inference, right? So this gives you an idea of your DRAM access. And so the reason for this is that all metrics should be reported for a fair evaluation of the design trade-offs. So we all know that when you're in the design space or engineering space, you have to trade off something. And so by asking questions about this whole comprehensive set of metrics, you can get a better idea of what trade-offs were actually made to achieve this. And just to give you an idea, here are some examples of what can happen if a certain metric is omitted, right? So for example, if people quote you without the accuracy of a given for a given specific data set or task, so if they just say, oh, it's this accuracy, but they don't tell you what the task or data set is, we could actually run a very simple DNN on a platform and claim very low power, high throughput, low cost. However, when you actually want to use the processor for an actual meaningful task, it's not actually going to line up, right? So if I give you, for example, digit classification task, and I say it's super low power for that, when you go to an image classification task, the power might blow up. So it's important to have an idea of what the task is and what the accuracy is. If someone were not to report the off-chip bandwidth, you could also play this game of I can build a very efficient processor with only multipliers, and then I can claim it's very low cost, very high throughput, very high accuracy, and very low power, chip power. But then when I put it into a system and connect it to DRAM, the overall system power is going to be very high because a lot of the power is going to come from that off-chip memory device, right? And again, are the results measured or simulated, and what test data was actually used? So I just want to really emphasize it's important to ask all these questions when you're evaluating solutions, and if you're in the space or you're providing a solution, it's important to report all of these. And so with all of these pieces of data, one way that you can go through these different pieces of metric to decide if a viable solution is possible is first you might want to ask, accuracy, what is the accuracy for a given task? And this tells you, is this system good enough for what I need it to do? Then you might want to ask latency and throughput, and that will determine if the system can run fast enough in real time. And only then, maybe you would then want to ask, what is the energy and power consumption? Because that will dictate the form factor of the solution. And then finally, you want to ask, okay, so if I hit 1, 2, and 3, how much is this going to cost? That will be primarily dictated, for example, if you're doing custom hardware, the chip area, and that will dictate how much you would pay for the given solution, right? So you can see how if you go through kind of this process of asking these questions, you are able to fully cover what is actually going on and determine whether or not this solution is good enough for your application. So to summarize, DNNs are a critical component of the AI revolution. They really achieve record-breaking accuracy for a lot of AI tasks, and that's why we're all really excited about it. But the computation cost and complexity is very high. You can see that's orders of magnitude compared to things like video coding. Efficient processing of DNNs is a very important area of research and in industry. And there's a lot of innovations at the different levels of the hardware design, from algorithms down to the hardwares. And there's also some device work, which I haven't talked about today. But then when you're considering different DNN solutions, you need to evaluate across different workloads and ask about all the various different metrics like accuracy, speed, energy, and cost. So some references for this particular work. So I pointed to this overview paper that we've put together a lot, so I would encourage you to read this if you're more interested in the details of this. Also, if you want to learn more about IRIS or have a more comprehensive set of tutorial slides, you can go on the IRIS website. We also run a professional education course at MIT twice a year. So if you want to figure out more about that, this would be a 2-day course. So if you want more of this, but expanded over 2 days in more detail, I would consider you to visit there. And of course, some of this work is coming out in the next couple of weeks and months. So if you want to keep up to date with that, you can either join the mailing list or follow us on Twitter. So that concludes my talk, and I'd be happy to answer any questions about this, any of these topics.
If you have questions, please line up at the microphone back there, and we'll take them.
Thank you for the framework and how you evaluate the different metrics. I was intrigued by one of your slides where you were lowering the latency, but also increasing the accuracy. Was that because you were training it so that it could?
Yeah, so there's certainly, in a lot of these cases, what you do is you start with the pre-trained network, and then you change the network itself, but then you're going to have to fine-tune the weights of the network. So you have to do some kind of retraining to readjust the locations of the weights. And in that particular example for NetAdapt, as we were pre-training it, or retraining or fine-tuning it, the accuracy actually went up a little bit.
Hi. Thank you for the talk. I have also used the energy estimation tool that you guys built and presented at the SLMR conference. I found it to be very useful.
Hear that.
And my question is about energy-aware pruning, where you mentioned you remove the high-energy weights. How do you determine what a high-energy weight is? Is that the one in the kernel that changes more often, so you have to fetch it more often, or?
Yeah, so that would be one particular way of measuring that metric. What we did was we did it at a higher level, which was we just basically looked at the layers that consume the most energy and pruned those first. So for example, one big shift that happened was that we ended up pruning the convolutional layers before the fully connected layers. And that's one big difference between energy-aware pruning versus magnitude-based pruning. And so in the convolutional layers, yes, those weights, you would have to fetch them more often and so on. So each of those weights are used many times. Right, so those weights become more energy costly, right?
Okay. So yeah, it's the opposite of something like weight sharing, where things are like the same, like the range of weights are
So it's a little bit different for weights. So this is like removing, removing each weight or how often a weight is used. Weight sharing is a little bit different. Weight sharing is basically saying that all of these different positions use the same weight value.
No, I mean it's opposite of the weight sharing process. Is something counterintuitive or like opposite to the weight sharing process, where when you weight share, you assign all these values to be similar, and then you prevent kind of fetching them. But you look at the weights, and the weights that are changing more often, you decide not to
Correct.
Use them.
Yeah, so in the weight sharing case, you would try and remove the weights that are used or shared most.
Okay.
That would have the highest impact, yeah.
All right, thanks.
Thanks.
Thanks for the comprehensive presentation. You mentioned that your group has done energy-based pruning. I'm wondering if you also do accuracy-based quantization, or either nonlinear or dynamic quantization. Could you comment the benefit of that when it comes to energy saving?
Sure. So we personally haven't done anything really on the quantization aspect, but there's been a huge amount of research on looking at precision. So I think there's various ways that people are doing it. Some they're trying to, kind of gradually reduce the bit width. So they're typically around like 8 or 9 or 10 bits, and they try and adjust the the bit widths, either of the weights or the activations of both per layer. Then you have the folks who go to the extreme and they do binary weights, which is the binary neural nets. And there, what they now have to do, so when you went to the extreme from like Joshua Bengio's group in 2015, you have a huge drop in accuracy. So now they're starting to add a bit of complexity back into it to try and recover the accuracy. So for example, XNORNet looks at, effectively, it's still binary weights in the sense that there's only maybe one or two weight values per layer, but then that you can scale and have a different scaled weight per layer. Right? So that's kind of trying to find an in-between and try and recover the accuracy that way.
I see. Thanks.
Sure.
I have another question. This is with regard to sparsity computation. When you design the row stationary architecture, I noticed in one of the slides actually says that it's actually skipping the access, the register file access for the zero coefficients.
Correct.
Is it just the memory access or also the computation?
And also the computation.
Also
both.
the computation.
Right. And that's in Iris.
And that's done for both the activation as well as the
So
weight?
in Iris V1, we only do that for the activations. And then in V2, we do for both weights and the activations. But there's been a lot of work looking at both weights and activations as well. So there's some work from NVIDIA. SCNN also looks both weights and activations.
Okay, great. Thank you.
Hi, nice
Hi.
presentation.
Thanks.
For energy-aware pruning, right, is it correct to assume that you're also doing retraining after the pruning?
Yeah, so you always have to like fine tune, right? In general, I think if you look back at the Jan LeCun slide about optimal brain damage, if you always fine tune your weights after you prune, then you can recover your accuracy more. So in all of these cases, while you're pruning, regardless if it's net adapt or energy aware pruning or even the regular magnitude-based pruning, you have to be in the loop of fine tuning the weights so that you can recover some of the accuracy. It's very rare, very difficult to say, I'm just going to prune a network and not update any of the weights.
Okay, all right, thank you.
Thanks.
All right. Well, thank you, Vivienne.